All right. Okay, so we have covered oil and gas, Chapter 7, and last lecture on Tuesday, we went through the problem set, assignment 1. A few students said it's always easier when you're seeing it done, and it's the same thing as anyway. You know, like watching Michael Jordan dunk a basketball and Mick Jagger sing looks a lot easier than actually doing it. So, but it just takes practice. Not that I'm ever going to dunk a basketball again, but these problems, though, I think once you get the routine of doing the units conversion, it will become routine. And that's really the point. And once you become bored at it, then you know you've learned it. Okay, so we're going to move on to Chapter 8, and you can see right here, these are these are the lectures. Let's see, 3, 4. I guess this one was from a prior. This was from a prior year, but these are the 2016 lectures. I don't know how that guy snuck in there. Oh no, that's correct. Yeah, that's all correct. Okay, here we are in week 8. Yeah, these are the 2 problem set reviews that I gave last time, and so today the exam should open. I'll just double check that while we're thinking about it. Timing is everything. That one looks correct. Yeah, there we go. Okay.
Success.
Yeah. And normally there's a third box here to allow it to stay open longer, but anyway, go ahead and knock that guy out. So I'm going to open up the figures for Chapter 8. Start banging through those. And again, Chapter 7, the odd chapters tend to be the science chapters, and then the even ones, 8, for example, is more of a technology chapter. I was looking over Mark Olson's notes from a couple of years ago, and he was diving pretty deeply into some of the equations here. And maybe what we'll do, just to remind me, page 300, there's some equations to calculate thrust. And it ties in fact, it ties in some of the concepts we were going over last time, the correlation between power is to velocity as energy is to distance. There's some nice physics in there, and we can look at that for a second, too. It'll have relevance. I've been following Elon Musk a lot lately, and really hope to see more electric cars, Tesla's being among them here in Montana, and he's also done some amazing things with rockets, and so that's relevant, obviously very relevant for our day and age.
I think Ford just committed to producing 5 million electric cars by 2030.
Wouldn't be surprised. Yeah, there's some.
They're seeing that market open.
Chevy, up. Yeah,
Bring the Bronco back.
Chevy's making some
And the
electric cars. Yeah, the Volt's making a big push too. All right, so start off a little bit of history here. Nicholas August Otto, German engineer who designed the commercially successful 4-stroke internal combustion engine. So if you remember back a couple chapters ago, we looked at the savory miner's friend. That was more or less an external combustion engine. Remember, the fire was on the outside of the vessel. So what Otto and others have done is said, well, if we can stick the fire inside a chamber, maybe we'll get a little more bang for our buck. All of the engines that Watt was developing, and even remember the Trevithick guy driving down the streets of London or Canterbury or whatever it was in the Christmas of 18 or 17. Well, at least 200 years ago, all external. Now, here we're looking at an internal combustion engine. This is a conventional, typical 4-stroke engine. So what we see is an air and fuel mixture coming in. So these are in an appropriate proportion. We've done a little bit of stoichiometry. We've looked at hydrocarbons. This is mainly octane, maybe some ethanol, along with oxygen. As this comes in, what you're really looking for is a nice homogeneous mixture so that when ignition happens, right here at the top, they're showing this compression stroke. And so really, just as this fuel and air mixture is at its maximum pressure, both valves are closed, spark plug goes off and drives it down, and actually, pushes on the cylinder with a downward force. So what we're looking at right here, remember we covered turbines a couple weeks ago. We looked at radial, axial, circumferential. This is a force. If it were to go off right here, that would be bad. If it were to go off over here, that would also be bad because it would drive the engine backwards. So the timing, your timing belt and your engine, all that is very critical so that the spark happens just after the cylinder passes what's called, top dead center, drives it down, and then sends this rotational energy. So you're going from you're starting here's chemical energy coming in, thermal energy, converted to thermal energy. That thermal energy is now converted into linear mechanical energy, and then into rotational mechanical energy that's sent back to the wheels, and away you go. So now you've got the exhaust in the chamber. As the piston comes back up, the intake valve closes, the exhaust valve opens, and the exhaust gases go out the tailpipe. So there it is, the four-stroke engine. There's also, and you'll see this typically on your lawnmowers. A lot of off-road motorcycles use this. Weed whackers, they tend to be a little noisier, run a little faster, but simpler in a lot of ways. So you just have this one inlet valve, more or less. The exhaust port is controlled by the cylinder itself passing back and forth. This is also why you have to put oil in your two-stroke engine, so the fuel mixture is actually lubricating the moving parts, so it comes down in this bottom chamber. And so really you have intake and exhaust happening at the same time. So as this intake is happening, the spark's going off, here goes the exhaust. As this cylinder passes by the port, up comes the fresh. And this is why the two-stroke engines tend to be a little dirtier. You get a lot of unburned hydrocarbons because this is just a boundary between these two fluids. So some of this junk stays behind, some of this stuff is wasted out the port, but
That's why they sputter a lot.
Sputter a lot, yeah. So there's the two-stroke engine. And again, we're going from chemical to thermal to mechanical. So here's Gottlieb Daimler of Daimler Chrysler, received his technical education in Stuttgart, went on to England to study the development of steam cars. So, we're talking right before the turn of the 19th century. 1886, he tried his lightweight high-speed petrol engine first on a bicycle. Not unlike, and you still see those around town. There's people in Missoula that drive gas-powered bikes. And it's also not unlike how the Wright brothers got their start. They were bicycle mechanics and said, "Hey, let's throw a wing on this bike and see what happens." But then said, "Hey, let's take this from a two-wheeled vehicle into a more stable four-wheeled vehicle." So in 1890, he starts the Daimler car engine. Yeah. All right. Let's go ahead and do. Yeah, there's a lot of really good math, and I wish we had time to cover all of it in class today. Let's just work through one little problem here, so we can get between velocity and energy. important concepts. So I'm just going to work through box 8.2, and I encourage you to just work through this with me with your own pencil and paper. Pencil, right? Not pen, Robert? Pencil and paper? Pencil and paper? Okay.
8.2, you said?
Box 8.2 on page 281. So this would be, if you're sitting there working for Daimler Chrysler, this would be the type of calculation that you would be expected to do. So what we're looking at in automobiles is kinetic energy. So E equals 1/2 mv squared. And we've gone through all of the dimensional analysis and units analysis. We know that m has dimensions of mass. We know that velocity has dimensions of length per time, so energy has dimensions of mass times length squared over time squared. So that checks out. So mass times length squared over time squared. That's energy. So the more massive the car is, the more energy it has. The faster it's going, the more energy it has, and it's a function of v squared. So there you go. And that's why in the 70s, when the Carter administration said, hey, let's all drive 55, you're going from, here's your 80 miles per hour, here's your 55. The energy requirements are significantly less. The velocity only changes by this little amount, but the energy changes by this larger amount because of the v squared relationship. Okay. So what we're looking for, let me just read through this guy. It says the 1903 Mercedes set the performance standard of a modern car. 60 horsepower engine would be small, and a top speed of 125 kilometers per hour is slow. Despite the speed limit of 70 miles per hour on UK motorways, why is all this power needed? Why don't you just still have the petite voiture of 3.5 horsepower? It says the key reason is speed. The engines must be able to accelerate the car to climb hills, because you're overcoming potential energy there. It's just moving its mass. But if we look at mass and kinetic energy, so let's just say a car, so the mass of a car equals, this is actually kind of a small car, 1,000 kilograms. This is about the mass of that 72 VW Beetle we've got sitting out back, maybe a 1-ton car. And the velocity of the car equals 30 meters per second, right around 70 miles per hour. So from there, it's pretty simple. We just know we want to know what the energy is. Energy equals 1/2 times 1,000, and I'll keep the units in there. Kilograms times 30 squared times meters per second squared, and the answer comes out to 450,000 joules, because a joule is a kilogram times a meter squared times a second squared. And I'll just write that out. 1 joule equals 1 kg meter squared per second squared. So it's not much. It just means that if I have a 1 kilogram object traveling at 1 meter per second, I can even demonstrate that right here in the classroom. I'd say my wallet weighs about 2 pounds. Yeah, so
Looks like a Moodle page.
it's full, just like the Moodle page. So if my wallet is moving through space at 1 meter per second, and that's about right. 1 Mississippi, right? I went 1 meter. That's a joule. Put all those wallets in the car and some plastic and some steel, And what you end up with is 450,000 joules equals 450 kilojoules. How many megajoules is that? Megajoules are bigger than a joule. They're also bigger than a kilojoule. So how many megajoules are we looking at?
Maybe 0.45.
Yeah, 0.45. Yeah. So if this gets if this gets bigger, since a megajoule is 1,000 times bigger, this has to get 1,000 times smaller. Here, I'll show you. I'll show you. That's fundamental.
Yeah.
That's fundamental. So we can go back and say, we'll just go back to the money analogy. So if I said, let's just say I have 1,000 pennies, 1,000 pennies. And I want to know how many dollars that is. Right away, you're going to go, well, it's not going to be more dollars, it's going to be less dollars. And you know, if there's 100, and you're just going to say, well, that's just $10. So if these guys get confusing, just go right back. Yeah, just go right back to money, because you know that the megajoule is bigger than the kilojoule, and you know that the dollar is bigger than the penny. So when the number gets smaller, the units get bigger, and vice versa. It's that simple. I mean, that is the entire reason for using the powers of 10. So you don't have to say 10 quadrillion, 777. You know, that's the whole reason. That's the whole
Also,
reason.
when it comes to money, you know, when they use K for thousand, like 100K.
Yeah.
And then use M for million.
It's true.
Megajoule.
Yeah.
Yeah, that makes sense.
Okay, so 0.45. Now, how does that compare to the USDA energy? What do you eat? What do you consume in energy per day?
Oh, calories.
200 megajoules.
200 megajoules is the technological. Yeah. What's the metabolic?
10.
10 megajoules. Okay, so how long is it going to take you to stop that car? If it's you versus the tug of war car.
Geez.
You're looking at
Maybe
10,
about an hour.
Oh, I see what you're saying.
about a half hour.
Yeah.
Oh.
Yeah. So
Too long.
little too. So that's why you lose the battle with the car when it hits you, because you are not strong enough to stop that car. I mean, you could if the car were attached to a giant rubber band, and you were like digging in your heels, but it would take you 30 minutes to slow that car down.
Wow.
Using your 100-watt self.
And depending on your mass and density too, you're like Superman or something.
If you were Superman, you would just blow it backwards with your breath. But
Yeah.
question?
So the way that you figure that out is by the meters per second, like how the joule equals 1 meter per second?
To get to how long it would take?
Half hour?
Yeah, let's do it this way. Let's do it this way. So if we're looking at 10 megajoules every 24 hours, and the car is running at 0.45 megajoules, the question is, what's this number? So you can rewrite that. You can rewrite that as so. X over 0.45 megajoules equals 24 hours over 10 megajoules. Right, it's the same equation. I just moved everything around here a little bit. Oh, there's Lori's name, Y-U-N-G.
Y-U-N-G.
Y-U-N-G, yeah. So in this case, X equals 0.45 megajoules over 10 megajoules times 24 hours. So the megajoules are going to cancel. Let's run that. Times 24 hours. 0.45 times 24 divided by 10 equals, closer to 1 hour. Closer to 1 hour. Yeah. That was your guess initially?
Well, yeah, because I just thought .45 goes into. 10.
20 times, yeah, there you go, yeah, nice, perfect, yep.
Based on how
Yeah, perfect, about 1 hour, nice.
So you use the, sorry, you use
Good.
the 24 hours, rather than the meters per second? How do we do that?
Well, so it's a kind of an odd comparison I made, but the point I was trying to make is like, how much energy is in a car? And it actually gets back to that summary one. And to do so, we just said, well, how much kinetic energy is in the car? And that's, that's pretty straightforward. 1/2 mv squared, that's the mass of the car, that's how fast it's going, 60 miles per hour. And boom, out pops 450 joules, because we know 1 joule is 1 kilogram squared per meter second squared. Put that into kilojoules, then finally into megajoules. And we don't usually use the word megajoules in our everyday language, but in this class we do. We know that 10 megajoules is how much food you eat per day. And so I just wanted to compare the chemical energy consumed by a person to the chemical energy in the car, because that's where it's coming from. I mean, there it is. Here's the hydrocarbons coming right into the car. Hydrocarbons going into us are, the breakfast cereal and the cheeseburger and, whatever you eat. Here's the car, eating and breathing, and we do the same thing. So I'm making a comparison there between the two and saying if you are burning 10 megajoules every 24 hours, every 24 hours, how long is it going to take you to stop that automobile? It'll take you an hour to slow it down.
And that would burn the equivalent of,
Half a megajoule. Yeah. Probably a bowl of Wheaties.
yeah.
Okay, so let's take a break there. That's a good place to stop, and we'll get into some other cool stuff.